it would be completely different point of view. So it would not be martingale. But when there is a connection, I will emphasize connection with what, sorry, it was Grigory was telling about this. I would emphasize connections with what you were doing. So it's exactly the same setting. This is a paper which Sinai wrote back in '95. The paper of Kiefer, which was mentioned by Yuri, was inspired by this paper. So we were both visiting Princeton at the time, Kiefer for half a year, I was there for 2 years. And that's when Kiefer wrote this paper after this kind of Sinai asked the question after his paper. So basically it's a question of weak disorder or diffusive behavior of random walk and random potential of directed polymer in higher dimensions, in dimensions higher than 3. And by the way, I think that here we would answer one question you asked in one of the lectures, but let's see how it is. So we have the letter ZD. And, well, Sinai called it F, so let us call it F as well. So there is a random variable at every point of this lattice. So basically, we have considered ZD times Z, which will be time, and actually it will be natural numbers, we'll not go for negative time. And at every point, there is a random potential. So we'll have f xi ix. So I belongs to Z, and x belongs to ZD. And that is, sometimes we will not write omega, this collection of independent random variables, parameterized by this lattice ZD plus 1. So it is IID sequence of random variables. So that's how environment is giving to us through this random potential, what is called disordered environment. And then you consider directed polymers. So you can go from any point to any other point. And so I divided at the moment, but the main object here will be so if we consider the path gamma, which goes on a lattice from point x at time k to point y at time n, so it's a path of length n minus k. K and n are two integer terms. Let me just change it to xi. So for any path, the statistical weight of this path will be given by pi gamma, and this pi gamma is equal to exponential. Here put sum of f gamma I from k to n. That is statistical weight of the path. And let me divide it also by 1 over 2d in power n minus k. So this is just would be probability of this path of a simple random walk if it goes for particular path of a simple random walk.
It would be on the lattice, jump.
It's on the lattice, yeah. So this path goes jumping every time to nearest neighbor on a lattice. So you will have this stupid parity thing, even on odd things, but it will not be essential for us. All right. Now, the important notion is partition function. It's normalizing factor, which we will have here. And partition function, again, parameterized by xk and yn. This is exactly equal to sum over all paths gamma going from xk to yn. So paths of length to dn minus k. And we just take sum of the statistical weights of these particles, of this path. And so that's partition function. So partition function over point to point. So we will prescribe final position of this path as well. Or we can consider also partition function of step n, and just by xk without prescribing y. So it will be just sum of these partition functions over all y. So So we consider all paths of length n, and that will be the partition function. All right. And so the probability distribution of a path. So what is a directed polymer? What is a measure which we call directed polymer measure? It is probability distribution P on gamma, which is equal to pi of gamma divided by partition function z x k n. So the starting point of the path is at point x at time k, and then you evolve it for time n minus k, and you're not prescribing here any position of endpoint, can be anywhere, and that's probability distribution. That is directed polymer measure. Measure. And we'll be interested in behavior, what are the statistical properties of this measure when xk is fixed and then goes to infinity. And what we want to prove is that this probability distribution of the path converges to basically to normal random walks. But we will be looking at particular characteristics. We would look at a central limit theorem for the endpoint of the polymer, right? So the endpoint of polymer is a position at time n. And so there is a probability distribution here, which is given by, so if we take y equal to gamma at n, then probability distribution of xk yn is equal to sum of the probability distributions of omega of gamma. So let me write it down immediately. So it will be z partition function of xk yn divided by partition function z xkn. So that is statistical way all the passes which come to a particular point, and that's statistical way of all paths when we take sum of all. So we are interested in these characteristics of the thing when n goes to infinity, and we want to say that y would have, that this P would have Gaussian behavior if you normalize it properly, normalize it on square root of n. Even more so, I would say that people who know what is random walks in random environment, where environment is given by transition probabilities being random rather than potential. So there are two settings in the theory of random walks in random setting, disordered media. You either prescribe random transition probabilities at every point of a lattice, or you do it through the potential. So in order to calculate statistical weight, you have to calculate sum of all the thing, and then you know what is statistical weight. So in the case when it's random transition probabilities, you also would have statement of a type I'm trying to prove that the endpoint of the corresponding path will behave diffusively in high dimension, in dimension greater or equal than 3. When disorder is small, you will have this statement. However, in this case, the covariance matrix, which is non-random, of kind of homogenized covariance matrix, so it would have Gaussian distribution, but the variance will be non-trivial function. It will be non-random, but non-trivial function. Here, variance will be the same as for simple random walk. So there is no changes of the covariance matrix. Covariance matrix in this case is exactly the same as. So it's very simple situation, and we want to get simple proof of this fact. So we want to prove that this y would have Gaussian, we'll say y minus x, what we want to prove, that y minus x divided by square root of n converges to normal distribution with prescribed variance. Converges to normal distribution. That's our aim. But what will be essential for me is not even this thing, but how we treat this problem. So basically, we want to understand what is the behavior of this partition function, this or that partition function. Okay. Now, what are the assumptions on f? It is assumed here that f would have exponential moments. So e to the f has second moment. Now, this probably definitely can be weakened, but we're not doing it here, so we will assume that expectation of the e to the 2f is finite. So we'll need variance of e to the f to be finite, and that's our assumption. And so,
Question.
yes.
So your claim is if you fix the environment and
With probability 1, so you fix environment, with probability 1, this thing would converge to normal distribution and then goes to infinity. For almost all environments. And since you have kind of discrete set of points, so you can say that it will be true for all points simultaneously. So I mean, for all points x and for all moments of time k. So all of them will converge to normal distribution with probability 1 altogether. So you can get a set of full measure altogether. But that's trivial. It's not that very essential. All right. So so let's remember what was what we discussed before. It was free energies. You call them free energies, right? Free energies were two free energies. So you take partition function, you take logarithm of partition function and divide it by n, and it converges to a limit which is called free energy. And this free energy turns out to be non-random. It's called self-averaging. This is what is called quenched free energy because you do it for given environment. And there is so there are two free energies, quenched and annealed. So in one of them you take z, take logarithm of z, divide by n, and it converges to a limit. You can take averaging of this, and with respect to the environment. It converges to the same limit, and this limit is called free energy, f. And I don't have parameter here because usually it's parameter beta, but I don't introduce parameter beta, so it's just a number. Or you can do different things. You can average z, which is always easier to do than logarithm of z, and then you take logarithm and divide by n, and that's quenched free energy, and that's annealed free energy. There's two free energies. And this usually all very simple to calculate. We'll do it in a moment. And the thing which was discussed by Grigori was that situation of weak disorder, which means that you have diffusive behavior, corresponds to a situation when these two numbers coincide. Or basically the fact that free energy, partition function of the model, of quench model and annealed model grow the same way as n. And so if you take ratio of them, it has a limit when n goes to infinity. And we already did it through martingale, saying that this is the martingale. So there is a limit of this thing, order 1. So here I would have the same thing. So what I will have here is, I would introduce lambda. It will be expectation of the exponent of f. And then I would have also a small lambda, which is expectation of the square of f minus lambda square. So it's a variance, a second moment minus square of the first moment, and then normalize it on square of the first moment. So that will be small lambda parameter. And other thing which I'll need, I'll consider, so that's one thing I have to introduce, but I'll use it. Another thing is Q are transition probabilities for simple random walks. So Q NZ is a transition probability of simple random walk going from the origin to point Z at time n. For simple random walk, you don't need to look from x to y. I mean, everything is translation invariant. Everything is homogeneous. So that's transition probability. So it's a sum over all gamma from 0, 0 to Zn. And then here, each of them comes with coefficient 2d in power n. So that's transition probability for simple random walk. It's a well-known object. We know everything more or less about the thing. It's classical object of probability theory. And what I'll need the following thing, that simple statement that sum of the QNZ, square of QNZ, sum over OZ on a lattice, and sum over ON from greater from 1 to infinity. this thing is finite. This thing is called, I call it alpha. It depends on dimension. And this thing is finite. It's less than plus infinity. And this is true when dimension is greater or equal than 3. That's where dimension greater or equal than 3 appears here. So it turns out that sum of the thing is, these kernels are summable in dimension greater. You can see it very easily, so let's just check it somehow. So Qn, simple random walk, behave diffusively. So basically what happened with the thing, that after time n, everything is distributed in a ball of radius square root of n, or the square root of n. So it would be, number of points here will be n in power d over 2. That's the volume of this ball. So that's where the bulk of probability will be. The probability will be here distributed. Now, the maximum of this quantity, so the maximum of Q and Z is known to correspond over OZ, is equal to Qn 0. Its maximum probability is to jump left be on the same point. I mean that n is here will be even, otherwise you will be in nearby point. And this thing is behaving like 1 over n in power d over 2. Actually, in the whole of them, they behave like 1 over n in power d over 2. They're more like uniform, but the maximum is at that point. So if you want to look at this sum, you can say that sum n from 1 to infinity, and then sum of z, qn square z. You can say that this is less or equal than maximum over all z, qn z, times sum of qn z. Right? And then sum over n. That's trivial. I didn't do anything. I just replaced square by the maximum term and the sum of the rest. But this is equal to 1. So this is exactly equal to 1. So I can immediately say that this is sum over n. And this thing is of the order of constant divided by n in power d over 2. And you see it's summable when d is greater or equal than 3. 2 is a special case, as usual. This is divergent, but very weakly divergent. And 2 is most difficult case, special case in many of the considerations of this type. So I'll need this number. And so the precise statement of a theorem will be the following. That I want to write it explicitly. All right, so I would put it the following way. So that would be say, assume, so that's a theorem. Assume that alpha, that lambda times alpha d is less than 1. Then for any f, which is a function from Rd to R is compact, so continuous compact support. Sum of the values of this function along y minus x divided by n minus k square root. That's my square root, that's my time. It will go to infinity. I multiply by square root of d, because we're in dimension d. But that's standard thing, because variance is like should be multiplied. You multiply in order to get simple variance. This so then I take this, I multiply it by z x k y n, and I divide it by y over z n x k. So that is the probability of ending at point y.
Sum of y.
Sum over y. So I just take average of this observable f for the endpoint of the polymer. So I want to say that endpoint distributed with Gaussian law, so this should converge when n goes to infinity, so the limit will converge when n goes to infinity, to integral of f on z e to the minus z square over 2 dz over 2 pi d over 2. So that's the theorem, and we'll just we'll prove the theorem.
There's no lambda or anything.
No, that is, lambda comes here with this assumption, lambda alpha d. So you exactly say how small you want to be. So there are two cases. We'll just discuss this condition. But you can care about this. You can either have situation when lambda is small. And so for any dimension, when lambda is small, this will be satisfied. Right? I mean, so alpha d depend on the dimension. So it's a number.
Right. But the theorem says if lambda is small enough, you won't see it at all in the limit. You will just see what you get.
Absolutely, absolutely, exactly. You'll see normal standard random walk on this level, on your average observable, right? And that's where difference is, because if it would be just random walk with random transition probability, this will be with some non-trivial coefficient, which will be depending on the environment. But here it will just disappear. And so, I mean, it's exactly the same. If you do the same thing for standard distribution for random walk, so you also will be multiplying square root of d, you'll get exactly the same answer. So in this respect, it is exactly the same as for simple random walks. And so let's consider one case which maybe answered the question which we looked at yesterday. So let's consider the case when f takes two values, right? So f takes values c and minus c. So f is equal to either c with probability 1/2 or minus c with probability 1/2, right? And I'm claiming that so in this case, it's very easy to see that lambda will always be less than 1. So we can calculate it simply. So it would be, so what it will be, what we want to have? We want to have that it's less than 1. So lambda capital is equal to e to the c plus e to the minus c 1/2. And expectation e to the f 2f expectation would be equal to e to the 2c plus e to the minus 2c 1/2. And then it's what I'm saying follows from trivial inequality that 1/2 e to the 2c plus e to the minus 2c less or equal than 2 times e to the c plus e to the minus c square over 2. So obviously that this term is smaller than that because product term is not here. And it means if you plug it here, you immediately see that lambda is less than 1. So what it tells us is that if you take this Bernoulli situation, and C can be anything, then if dimension is large enough, this number is less than 1. So it means that in this situation, for D large enough,
Alpha D is decreasing? Yeah.
doesn't matter. Alpha is decreasing with dimension, of course, yes. And so for D large enough, alpha D times lambda will be less than 1. So when you asked whether there is a situation where this critical beta can be infinity, yes, it is infinity in such situation, right? I mean, you asked. I think you asked. Gregorio, who asked? He did. But I gave you wrong answer. I said that it was always finite. No, it's not true. I mean, it's in this situation. But for example, if f has Gaussian distribution, then it will not be true. Then you will need. Then it will be finite.
But if you, so you can increase C, doesn't matter at all.
Yeah, it doesn't matter at all because of this thing that this little lambda will be less than 1. Yeah, just all right. So if dimension is large enough, when so that no, I guess it's not true. I mean, if you're getting so it is less than 1, but it gets closer to 1, right? When I think when C.
Still, if alpha t is 1/2 or something, then you can choose.
Yeah.
You want.
Yeah. You're right. Yeah, you can choose anything. Yeah, it's true.
So how should we? A little bit confused.
Okay, so let's go for the proof. Okay. So what I will discuss, it will be several steps in the proof. But the main idea is that you express partition functions in kind of perturbation theory in L2. So you do perturbation theory in L2, and the series will be convergent series in L2, and you'll be controlling them in a nice way. So let me just start to do it. Right. So I would replace this order with something which is more convenient for me. I think I'm fine here. So I introduce kind of normalized disorder. Which will be h xi. Those will be my random variables. They will have mean value 0, because e to the f doesn't have mean value 0. And it will be like exponential of f minus lambda divided by lambda. So that has mean value 0. And so I would introduce so basically, partition if I would write expression for partition function, it would look the following way. So z xk, let me fix other endpoint yn as well. It is sum over all paths gamma going from one to another. Here you have exponential over sum of f I gamma I from k to n, and then you have 1 over 2d in power n minus k. And you write it as a sum, so it will be sum over gamma, and then it will be product of these individual terms. So we write it as a product of lambda plus exponential f minus lambda, product over all I from k to n, 1 to d n minus k. And then I would have this h, so it will have it sum over gamma, product ikn, and here 1 plus h gamma I. So I just divided by lambda, it would be 1. This would give me h, and I keep track of lambda, so it would be this times lambda to the n minus k. Maybe n minus k plus 1, so now I write n minus k plus 1. And how many of them? Plus 1, I guess. But
I think it's better to do n minus k.
Let's not go into ones. Ones are coming later. And so you have this thing, and you have 1 over 2d in power n minus k. Right. And so that's very standard thing in statistical mechanics. You then open brackets in these products, and you collect certain. So what if you open the brackets, you will have certain number of h's. So the main term will be 1. No h's, and then it will be 1h, and then 2h, and so on. And so that will be my perturbation theories. In the powers of h coming to this expression. So it will be, so when I put 1, what will be the main term? It's 1 times 2 to the n minus 1. So it will be transition probability, right? So you take 1 over 2d n minus 1 and take sum over all. So you express this as 1 plus sum over r from 1 to infinity to n, or to n minus k. And this r is how many h's you want to keep in this product. So what I would write the formula for that. So the answer will be, the expression which we'll be dealing with all the time is, so you have lambda to the n minus k, and then you have qn minus k y minus x for simple random walks, and then you have plus sum of r greater or equal than 1, and then every term would have, you will have to pick certain number of times I1 and so on IR. So it would be sum over I1 less than I2 less than IR less or equal than n greater or equal than k. And then you have here sum over Z1 ZR. Those are points from which you will take H.
What's the Z?
So you take points Z1, Zk, which on points on the lattice. So what? Sorry, Zr. So you fix R moments of time, and you fix R points on the lattice, and then you take paths which pass from point Z1 at time I1, Z2, I2, and so on.
These are the gamma, these Z's encode the gamma. Yeah.
Well, the points I will call Z, okay, and that's point which is gamma at time I, gamma I S is equal to ZS, right? And so you will have here, so let's remember it, I don't want to have it. So you have product of, so let me first write transition kernels. So we will Q going from K, so Q, how I denote it, so it would be I1 minus K, and here will be Z1 minus X. So you first go from X to Z1, then you go from Z2 minus Z1, I2 minus I1, and so on. Q, the last one will be Y minus ZR, and here will be N minus IR. So this is all transition kernels, but this is kernels of simple random walk. So you count number of trajectories and what will be their probability. This product, because it's simple random walk, and then you multiply by H, product of H. I from 1 to R, H, IS, ZS. So that's expression for the partition function, right? Nothing happened. And so, 2D already incorporated in those things. That's transition probability. When you count sum, you take sum over gammas, so you take, that will be this kernel, so it disappears. All right, so let's look at this expression. So, of course, crucial fact is that all H are completely independent and mean value is 0. So this is in L2, these are orthogonal terms. All this is orthogonal. They're all orthogonal to each other. And it's very easy to, so if you take product of this two terms of this type, the mean value will be equal to 0. So when you start to calculate L2 moment, you have to take square of the thing. And so each individual term multiplied by another term of this type would give 0 because they have different collection of H. At least one H will be out of it. And so it will be mean value 0. And only squares of this thing will participate. That's exactly the fact that they are orthogonal. So I'm saying that if I take L2 norm of this expression, and mean value is equal to 0, so L2 norm will be just expectation of the square, it will look like sum of the squares, and this one would give us lambda, right? So second moment of h is equal to 2 lambda. So expectation of h square is exactly what we calculated. It will be e to the 2f, expectation e to the f minus lambda square divided by lambda square. So this is little lambda. And so what we'll get here, it will be lambda to the n minus k. And here you will have 1. Well, I mean, I would divide by q n minus k y minus x. And here would have 1 plus the sum from 1. So I take square of the thing. So it would be the square, and it will be sum of the squares of q squares. Times, so it would be r terms, r different of different q's. Of course, you have this sum over i's, ir, and sum over zr, and all of them would come with coefficient lambda to the r.
And then cross with the constant.
So that I should also divide by this term here, but I guess maybe I'll put it like this, then it's correct exactly.
These also are orthogonal, these two terms.
All terms here are orthogonal.
Also the first one.
The first one because mean value is equal to 0, right? And so this is if you think about this kernel of operator, this is just R's power of this operator. So this sum is bounded by so this thing is, so what I would say that the thing will be bounded by lambda to the R times alpha d to the R. So this sum is bounded by alpha to the d to the R. Individual term, if you take summation of individual term over z, it is alpha d, and you have product of R of these terms. So the whole thing here is bounded uniformly in n and k. So in L2 norm of this thing is bounded.
It's sum over R still.
It's sum over R, yeah, but this sum over R is summable, and you can put it up to infinity under condition that lambda times alpha to the d is less than 1. So it's a geometrical progression which is summable. So we're talking about bounded things in L2. And so what is the idea of further consideration? So what do you want to say about it? So what will give main contribution to this sum? So let's look at the picture, what's going on here. So I'm going from one point, from point x at time k.
I'm sorry, Costa, so what you're saying is the product is q squares, that's actually one q square, because it's a transition thing.
Sum of the q, so what we're using, the sum of the q square, q square of, how denoted, z n, zi over I and over z is equal to alpha d. And that is a product of these kernels, z2 minus z1 and so on.
Right, so this becomes one of the q squared.
Yeah, each of them is, each of them would give you q square. You kind of, so this is the norm of the operator. And this is us power r of the operator. So the sum of the thing will be bounded by alpha. If you take the sum over r, it will be alpha d to the r. You want to see it? So, I mean, it's not exactly, I'll tell you why. If I fix y, you don't see it. But if I'm not fixing y and taking summation over y, what will happen here is the following, that the last term is y minus zr. You take summation over y, you get 1 alpha d. The next term will be zr minus zr minus 1. You take summation over zr, this term disappears. And so every time one term will disappear, you produce alpha d. And then it's power r. All right. So let's look what is the main idea here. And the idea is very simple. So we have to go from point xk to point yn. And we do it in certain number of steps, say in r steps. It's not on a lattice anymore. So you pick some time and some point on a lattice. So you have kind of path, and every point here has time and point on a lattice. Time and point on a lattice. And so where the main contribution would come from? And the idea is the following, that the main contribution would come from the following thing, that you will have many steps. So suppose I is fixed. You have many steps near this point. Then you have jump to vicinity of that point. And then you have many steps here. So the contribution will come in from summation of this thing, which is actually partition function, which we introduced when we summed over y. Basically has the meaning of this partition function will take summation over all y's. So this will be variable which depend only on x. Then it will be summation over there, which will be similar partition function, but coming from kind of related to y. And then it will be one connection between them. And one connection between them will be transition probability of simple random walk from this vicinity to that vicinity. But the distance is order n, because here it's very localized. Sorry. We're considering situation that y minus x is order square root of n minus k. So we're in diffusive regime. So this distance is order n minus k. Distance between times is n minus k. And so it doesn't matter where you are, all transition probabilities are of the same order. So if you jump from this point to that point, or from this to this, it's the same thing. So it will be factor q y minus x n minus k, which correspond to one big jump, and then many little jumps which correspond to partition functions. Right? So let me make it more formal. So I introduce random variable phi and psi. All right.
So in that, what's R there? The number of
R is the number of steps. You will take summation over this, the number of steps. But in all these sums, so it will be sum over R1 here, sum over R2 here. Both of them will be going to from 1 to infinity. And then there's one step between them. And that's the main contribution to partition function.
And why this number of steps is not the difference of times? Why n minus?
No, the number of steps you're doing, you take summation of a number of steps, right? So what I'm saying is that everything you will have here for giving R would have the following form. It will be some R1 near one of them, some R2 near another one, plus one more. And they together, this is R things. So that will be the main contribution. And if you have two steps, then it will be smaller or smaller order term. Okay. All right. So what would be the exact statement in the following theorem? So let me introduce two things. Basically, I already discussed it. Phi x k. So it depends on one point. And psi yn. And that will be sum of r greater or equal than 1, sum of I1, and so on, IR greater or equal than k, but not restricted from above. Can be anything. Q, K1, sorry. K1 minus K z1 minus x, so in q k, sorry, I1 minus k, and here will be IR minus IR minus 1, Z R minus ZR minus 1. So this is again product of this of this Z, and then I multiply by corresponding H, Z1 I1, and so on, ZR IR. So it's similar sum without lambdas, but it's similar sum. And what I explained before, that this is summable thing. The thing exists in O2. It's convergent in O2. So this is a random variable. And it depends only on x account, because there is no other point. So that's exactly what I meant by summation near this point.
There's also sum over Z.
Sum over Z as well. Yes. Sum over all Z. And similar thing here, just going in opposite direction in time, right? So you're just ending in this point, but you make several jumps over there. So expression here for psi will be sum r from greater or equal than 1, sum k1 kr less or equal than n, then going in opposite direction, I1 IR, and then you have similar sum over Z1 ZR, and then you have similar expression here. The last one will be k I2 minus I1 Z2 minus Z1, and so on, and here it will be n minus IR, and here will be y minus ZR. And here H, Z1 I1, H ZR IR. So it said one corresponds to sums going from this point xk, but not requiring you to go anywhere. The other one going from point yn in opposite direction. They have the same distribution, and both are convergent in L2.
Why you're compensating with this function h?
Oh, this is my randomness. That's the main thing. That's I'm not compensating. That's my randomness. So that's how expressions for partition function look like. So that will be important thing. So what is this? It's a random variable. It's actually a collection of random variables parameterized by x at k, identically distributed. The same is here. They're identically distributed. They're correlated, of course, and they have the same distribution, this and that, but that doesn't. It's not very essential for me, right? And so what I want to say is a certain expression. So what the main claim here is that partition function, which we have, our main object, can be expressed as a product of 1 plus phi times 1 plus psi. So this thing doesn't contain 1. It starts with ai equal to 1. So if you kind of think of partition function, it also should have 1. So 1 plus phi is a sum of terms here. 1 plus psi is a sum of terms there, and they're connected by simple random walk transition probability. I'm claiming that partition function that lemma partition function z x k y n can be written in the following form. It's lambda n minus k plus 1 times q n minus k y minus x times 1 plus phi xk times 1 times psi yn plus small error. The plus error, which is small, and this error term will be small uniformly in y. We'll think that y minus x is less or equal than some constant a in times n minus k. So if we're in diffusion regime, you fix constant a. So for any y in this thing, you have this formula, and this small term is uniformly small in L2. So factorization of partition function. So partition function, the main contribution for partition function, comes from the term summation here, which is this term, summation there, and they're connected to one big step. So you have to go from k to n in time. And you have this, so think about time only first. So you go from k to n. You do it in r steps. R can be anything. So you have to cover big space here. And we're claiming that the main contribution would come from just one big one, and then maybe many, many small ones. But these small ones give partition function of point xk, and the other. So that's the main factorization theorem. Actually, I think this is more important than the central limit theorem itself. The diffusive behavior is less important than this factorization. It easily follow from that. We'll get it. But I want you kind of believe me that this is very simple statement. You just don't have to do, there are no simple, extra ideas to prove the thing. To prove the thing, you have to use two factors. So there is summation in R in our formula for Z. There is summation in R. And so if R is very large, then you're kind of in trouble. If R is order n, then what means a big step? Maybe you cover everything with small steps. So you consider the case, two cases. So R less than some constant time logarithm of n minus k. It's the first case. And then R greater than constant times logarithm n minus k. So what means that you have to have small number of R, logarithmically small. If it's big, then you can write estimate. The whole thing will be sum of the contribution of these terms is bounded by alpha lambda d, lambda alpha d in power r, sum over r greater than b log n minus k. Put log n, k is fixed. So that will be estimate from above from these terms. And they will be very small because it's exponentially small thing. So if r is large, this will be small like some power of n. So you don't worry about these terms. They're not contributing. And then when r is less than logarithm of n, logarithm n, then it's basically order 1 number of steps. Then you can show that the main contribution would come from one big step. And that's it. I mean, there's nothing else. Now, next step, I would convince you that it's true that the main contribution in the sum comes from one big step. And then I think after that, you will believe that this statement is correct. And you see, if you have one big step, you have this one kernel connecting these 2 points. And the ratio of them is close to 1 uniformly, because you vary very little x and very little y. Because you made so there is another maybe technical step. You can say, what does it mean a big arc? You say that it's greater if the length of the arc is greater than n and some power beta, which is beta will be between 1 and 1/2. So that is a big arc. And you say it should be one of them, otherwise it is a smaller order contribution. That I will prove to you. Now, if it is one of them, then all the rest are smaller than n to the beta. So the total distance in time covered will be n to the beta times number of these steps r. So it's still less than n. So definitely the arc, the big one, will be order n, because sum of this one will be n to some power beta. Sum of this one will be n and some power beta. This is power beta. So it will be one step like this, and the ratio of transition probability is close to 1. So you can take it out of the product, and the rest goes to the error. Is it clear or not? So I'm trying to convince. Okay, let me repeat it. It's very simple. And so let me repeat it again. So as long as you know that number of steps is small, let's consider arc which is greater than that. Right? So if I know that there is only one arc which is greater than that, that this arc really is n, order n, not n to the beta. because all the rest are n to the beta times r. And this is less than n. So the thing is order n. And you also can say that corresponding z's will be not far from x and y. When you end up at certain point z here and here, which you connect, they'll be close to x and y. So you have to compare q n minus k y minus x. You can compare with q, this will be smaller, this will be some smaller arch, but also order n minus k. And probably Ln. And here it would be z, I don't know, z s plus 1 minus zs. Those s correspond to big arc. So this z will close to y, this close to x, so this ratio is close to 1. So I can take it out, and all terms here would contain one of those. So I just divide by this term, take it out of the product, and the rest goes will produce error term. So it's very simple, simple argument. The only thing I was to convince you that the main contribution comes from one big arc, because you can be in trouble if there are several of these big arcs. Then you're in trouble. And there is I'll put this argument forward in a moment, but I want to look at this formula and say, so what is this? This is partition function of the annealed model. That was partition function of a annealed model. So what Grigorij was telling us that if you take this partition function divided by partition function of a new model, the ratio tends to a limit. And the limit is given by this 1 plus phi, 1 plus psi, times these controllable terms which you have here. Right? It's also part, this Q is a part of a annealed model. Because this is partition function of a annealed model because we go from x to y. If there is no x to y, it's summation over y, then this will be partition function. But for giving y, that is partition function. And the ratio is this 1 plus phi, 1 plus phi is a ratio which tends to a limit. So you have control of this ratio. And phi and psi are local characteristics. They depend on the sum in some vicinity of point x and point y. So if you go away, the correlation will decay because of independence of your environment. All right? And now you can, so I'm claiming that this is most important thing, this factorization thing. And moreover, you can go beyond diffusive regime. So if you are really interested in diffusive regime, then you need to consider y minus x to be y to be in some vicinity of x. So you have to have this condition that y minus x is less than a times square root of n minus k. But in fact, you can have this factorization when points are farther away as well. Just this term will be not behaving like Gaussian term. It will be just transition probability from y to x in time n. It will be exactly the same formula. You can go beyond diffusive regime in this formula. That's why I'm saying that central limit theorem may be not that important to us than this one. Let me, before I'm explaining why it's one arc, which I'll do in a moment, let me explain why it's important. Okay. So I'll be dealing with this formula. And theorem I'll keep. We'll come back to it. We'll prove central limit theorem. But it's already incorporated as a factorization thing. And think for a moment that now I want to come back to Hamilton-Jacobi equation. So I'm solving Hamilton-Jacobi equation for Bürger's equation for quadratic Hamiltonian. So I have Feynman-Katz formula. I made this Feynman-Katz formula. I write solution for the corresponding heat equation. So how does this solution look like? Remember what solution of the heat equation was we're looking the following way. We had point x and time t. And when we want to write solution, this is another phi, I'm sorry about that, but it has nothing to do with this. So this phi xt, it was given by, so I was basically taking averaging. So it will be the following way. It will be look like z y n This will be time k maybe, to be consistent with what was before. So you consider all paths going down. Then they will be not simple random walks, but random walks weighted with our environment. So I would have the following. I would have and here I have initial data, which will be e to the minus 2 nu. Let me initial data psi of the heat equation, psi on x. So that's initial data giving that for the heat equation. So it's already multiplicative setting. It's not Hamilton-Jacobi, it's just a solution of the heat equation. Psi t is equal to nu Laplacian psi minus 1 over 2 nu f psi. So that's after Hopf transformation we get that, and we write formula, Feynman-Cut formula. So the answer will be here. You take sum over all x, and here you will have psi x time partition function going to yn xk, and that will be just 1 second. That will be partition function. That will be sum over all x, and all right. So actually, that will be expression for the solution. So if I divide by partition function point yn, take summation over all x, then it will be probability distribution on our direct polymer. Otherwise, it's in Feynman-Cut formula. You'll have to multiply on these partition functions. So that is the solution, right? And now this solution at point psi at point y at time t, time n. And now I want to compare solutions at one point and another point. So it will be y1 and y2 at the same time n. And so this will be y1 y1, y2, xk. But now remember formula for factorization. So this thing, for large values of n minus k, it would look like a thing which depend on y1, thing which depend on y2, and then thing which depend on x, but summation taking over x. So basically, if I take ratio of the thing, look at every individual term here. So it will be ratio of these two partition functions. The x term will disappear, will be the same here and there. And so it will be constant. It will be something which is basically psi y1 divided by psi y2, right? So it will be another psi, this psi which is here. So if I take ratio of the thing, it will be 1 plus psi at one point divided by 1 plus psi of another point. And you see that the ratio of psi 1 n, psi y2 n will be equal to, I'm sorry for this 1 plus psi at y1, 1 plus psi, let's say psi tilde, only for this form of y2, but it will not depend on initial condition. Dependence of initial condition will disappear because every term here, the ratio, is close to the thing. The sum divided by sum will also be close to the same thing. So this plus small times 1 plus small error. So what it means? It means that dependence on the initial condition just disappeared. So the ratio of the value of this function to points does depend on the initial condition. So it tends to a limit. You can start with one initial condition. Now, ratio, because we're talking about heat equation rather than after Feynman-Cut formula. If you go back, taking logarithm of the thing to the Hamilton-Jacobi equation, then the difference between them will not depend on the initial condition. And that's exactly what we say, because solution is defined up to a constant. So that's what is called one-fourth solution. You don't depend on the initial condition. So this is incorporated in factorization formula. The fact that it is Gaussian behavior is not even essential for me. Yes, I can go further and I can divide by partition function, and actually then it will be like Gaussian expression here, so integrate this psi with Gaussian expression, but that's not essential. What is essential? Factorization formula. All right? Okay. But when Sinai wrote this paper, he was not interested in Hamilton decomposition, I would say. He was just interested by paper of Spencer Imbrie and by paper of Balthausen, and his motivation was to just understand what's going on and to get better conditions. It's a nice condition that alpha d times lambda is less than 1. So he went all the way to prove central limit theorem, and now I'm doing the same thing. So let me prove central limit theorem, which is written here to you. Okay? But I insist that the main statement is extremely simple, and this is a statement of this type, of factorization. Okay. So let me first prove what I wanted to prove, that this formula is correct. So in order to kind of explain why this formula is correct, I have to do one thing. I have to explain why only one big arc give a main contribution. So the trick here is the following. So so what is the main object when we write L2 series for these expressions? The main object is square, Q square. Q square of n z, that is the kernel which we have to sum all the time. This is the kernel which we are studying. Not Q, but Q square. This is not a probability distribution. But we can make it probability distribution if we divide it by alpha d. So then it's probability distribution of a Markov chain going from, so it's Markov chain in space and time, in jumping from point 0, 0 to point n in time and z in space. Because sum is equal to 1. So you have this kernel, next time you apply the same kernel, it's a stationary Markov chain. Right? Now this Markov chain has two coordinates, space and time. So what will be the, so if you think about this as probability distribution, so what is the probability distribution of large values of n? How it decays, this probability distribution for large values of that for this Markov chain? So you basically take summation over z and you see what will be, we saw it. It behaved like 1 over n in power d over 2. That's how this thing behave in large values of n. That's asymptotic behavior. So it's a Markov chain which is in time variable behave this way. Now if basically I want to consider this Markov chain and to go from point xk to yn. That's what I'm studying, of simple Markov chain, of giving by this expression. And I want to say that the main contribution comes from one big step and several small steps. So let's try to do simple calculation, and I think I will convince you that it is true. So let me do very simple calculation. So I have to go from point, let me put from 0 to k equal to 0. I mean, forget about k. It will be 0 now, right? In time. And suppose you forget about z coordinate. So it's a Markov chain in time only. So it's a transition you can do not on the nearest neighbor, but you can go to any, from given time you can go to any time, but decay like this, probability distribution decay this way. And you want to see what is it, how to estimate probability to go from here to here. Right? So if I would have steps here, so suppose I is equal to 2, but I can take any r, just for simplicity. So one step is less than n to the beta, because it's short. So it would be one step which is less than n to the beta, And then another step like that. Or you can have this step small, less than n to the beta, and then this one big step. Or you can have two big steps. And two big steps is that there are two steps which are larger than n to the beta. So I would consider two big steps. And so what would the probability here? So it would be 1 over, the first jump will be 1 over m in power d over 2 times 1 over n minus m in power d over 2. So that would be probability of jumps. And you have to take summation over m on this expression. And it's quite easy to see that if you take summation here, it's a finite sum. So the thing will behave like 1 over n in power d over 2. And if you have summation here in m, again, it is finite sum and behave like 1 over n d over 2. So this thing behave like 1 over n in power d over 2. But you have two things which are big. That will be much smaller because you have to have here summation starting not from 1, but from m to the beta. So you have summation over m greater than n to the beta. And the same expression, 1 over m d over 2, 1 over n minus m in power d over 2. And that is much smaller than this term, because it has additional smallness coming from this thing. And the same from other end. So I did it for 2r, but r are less than logarithm of n, so I can do a finite number of r, and this will be the same type of estimate. So it's very easy to estimate whether this Markov chain, simple Markov chain trick to estimate that this probability is dominated by one big jump rather small.
H is won't play a role.
H is not playing a role, it's just about kernels Q. It's not about H. It's about contribution coming. So H order 1. And when you calculate L2 norm, that's coefficient of L2 norm. And L2 norm coming from the summation of the two arches is small compared to the one norm. And that's it. That's factorization statement. There is a little bit of standard technique, probability technique, because in fact you have to consider conditional distribution going from y to x, from x to y, and you have to condition with respect of space variable as well. I ignored space variable here, but you can do it. I mean, you can do this estimate. It's standard thing, because we're talking here, there's no randomness. We're talking about concrete this probability distribution. We're studying what's going on with this probability distribution for these kernels, and we're studying this question. It's not a question about disordered media. It's a question about simple random walks. But
you need to control these agents, right?
there's no, okay, once again, how the sum looks like. So that you have individual terms, and that's L2 norm of individual term with a product of h's. You have many, many terms. And I'm saying that all the terms corresponding to several big arches have L2 norm smaller than the answer. So you can divide by the answer and put 1 plus small correction. It is indeed, the sum is indeed the L2 norm of this term. So that's, there's no cheating here. That's very as simple as that. Mm-hmm. And so the last thing is just to show that, that there is a central limit theorem. But that is almost obvious, because what you have here is this factorization expression. So just incorporate everything there. So you start with, again, with this expression, factorization expression. So sum of z x k y n divided by y to the n minus k plus 1, and then I take f x minus y minus x divided by square root of n minus x, or n minus k square root of d, and take sum over all y. I can write it as 1 plus phi xk, doesn't depend on y, and then I will have sum of q n minus k x minus y, y minus x, f y minus x square root of n minus k square root of d, 1 plus psi yn. Plus small error, which I'm not writing here. And actually, the central limit theorem comes just from this term, with this one. This would produce the integral I wanted already. And then you have to show that sum with this thing will be small, will be close to 0. But remember, this has average value 0. So you have a thing with average value 0, and sum of the probability is equal to 1. So of course it will be small sum. The sum of this psi will be small. So it comes small compared to when you get this. So the main contribution comes with 1, and if you take this random variable with mean value 0, then they will produce smallness. So there is basically, it's immediately, the formula already contains everything. And you just get the answer. So there's no mystery, it just is there. So it's a very simple problem. But first of all, technique of this, you see, there is martingale approach, which is very simple. You don't need to do any calculation. You can keep your hands not dirty. And there is these expansions in statistical mechanics. It has flavor of what is called cluster expansion in statistical mechanics. And this is a powerful tool which allows you to write convergent series which give you control on what's going on. So you see what's going on there. And that's what I wanted to present, that this is a simple statement about kind of simple problem. Now, at that time, nobody knew that there's a result about localization in dimension 1 and 2, what is called strong disorder, or localization in dimension 3 for large values of f, not Bernoulli, but other large values. It's much harder statement. But let me just make one comment, and then I finish. So basically what Grigori, it's a simple statement. It's not even mathematical. Well, we'll see what I would mean there. So remember that we were discussing this free energy, which will be annealed, and free energy was quenched. And the question was whether they're equal or not. So meaning that where partition function of quench grows like annealed or not. Now, so what does annealed means? It means that you're averaging with respect of environments. Quench, you're not averaging with respect to environments. It converges to something which does depend on the environment. You're not averaging with respect to the environment. But here you average with respect to the environment. So you explore different environments, and you average with respect of them. So now, look at the polymer. Suppose I have a polymer, and suppose this polymer doesn't have localization. So it means it spreads. Not necessarily like diffusion, like here, but spreads with time, like some power of m. So the bunch of trajectories have variance growing. They're just spreading in a space. So what is the partition function? You integrate e to the action over this path. But then, you know, I mean, since it's spread, you kind of consider everywhere. So this environment is independent of this environment. So you effectively, when you integrate over this path, you effectively integrate over different environments. And so if you have spread, then the quench should be equal to annulled, because it's effectively average in respect of the environment. But in fact, you can go farther than that. You can say that, and that's a remarkable thing. I mean, I wouldn't kind of had courage to go in this direction. In fact, you can say more than that. You can say that if it is not, if quenched and annulled are different, then they must be localized order 1. And that is a powerful statement which was proved by Comets, Francis Comets and Karmanahu. But there is not mystery here. I mean that there is this dichotomy of whether quenched is equal to annulled, dichotomy, your localized or your spread, it is the same basically dichotomy. So that's of course a convenient thing, because sometimes you can calculate the thing, you have control of them, and so it gives you a technical tool of providing localization result, although you will have no idea where you are localized. All the statements are extremely non-constructive in the sense that you know that you are localized, but you have no idea where. The method gives you that, but doesn't give you this. But that's how it is. I mean, so I wanted to finish with this observation that there is spread means that you are averaging in respect of different pieces of environment. But if you have no spread, then you explore one piece of environment. So there is no averaging here. And the result may be very different from that one. And in fact, it is in the strong disorder case. So it will be miracle if they coincide. But because yeah, I mean, yeah. All right.
Any questions?
Yeah, I was. So in your final proof of the central limit theorem, you said that the psi y term doesn't contribute because it has a
Zero mean value.
zero mean value.
And localized.
And the f doesn't matter because there's also y there.
No, but this is just function.
Right, but why does it, because f.
These terms are order 1. This is bounded function.
Yeah, but so I can imagine if you sum qi against psi I, you get 0 because they have.
It's smaller order than it will be smaller order. I mean,
Well, it's smaller order because it has expectation 0. That's what you're saying.
yeah, exactly.
But then when you multiply with the f, it no longer has expectation 0.
It is a 0 because it's not random variable.
But it depends on y. So
No, but y is the summation of all y's. So
that's the way I understood
only
it.
this thing depends on the environment. This doesn't depend on the environment. It's summation of all y's. All y's on the lattice.
Right. But so, I don't know, but maybe.
So take expectation of this term. So this is non-random term, this is not random term. Expectation is equal to 1. Remove 1, it will be 0. This is only random variable here. I'm taking expectation with respect of environment, not with respect of polymer.
That's what I was
Yeah,
mistaken
it's expectation with respect of environment.
because of the sum of all the ID things.
Well, think about L2 space, and they in value 0, so you have to take square, and then they start to cross products will be decay because there's decay of correlations. I mean, the usual stuff.
Any more questions?
Yes.
I mean, at the beginning you put this assumption that the environment must have this exponential.
Yeah, I mean.
And why you cannot get rid of this?
It's an annoying thing. Technically, it's much harder not to have it, but we were facing this difficulty in many situations, and it's annoying. But let me just tell that I can just think that my initial model is just product of h rather than e to the f. And then, of course, on h I would just need second moment.
Okay.
But this is as good model as as e to the f. So this is an existing technical problem. There are ways to deal with it. When I will discuss the next time intermediate disorder, it will be similarity with what I did here, and we also would assume exponential moments to make things easier. But again, you can introduce this similar nu, and then you just need second moment.
But of course, with the lambda, I mean, your condition even uses the second moment, the exponential moment.
Exponential moment, yes.
Yeah, but if you think that your model, forget about e to the phi, you just have this model with product of nus. So the weight, you have the weight of the path is product of nus along this path. That would be a model which would not require any. Yeah, it is a good model. But if you write e to the f, then you have to.
Let me rephrase my question then. So suppose we look at f, not at h. And are you saying that there could be f with?
Let me ask you, Gloria, do you need this? I think it's not needed really for the weak disorder, the exponential moments of disorder. I think that you don't need it, and I think maybe even I think that even Belthausen doesn't need it. I think, but I have to double check. My feeling is that it's not essential, but I would maybe be a bit cautious
now
here.
I have another question.
No, no.
Go beyond that. So what happens when your environment has no second moment condition? I mean, when you go beyond the Gaussian, when you have second moment, normally you think that Gaussian is the right limit, right? And when you don't have second moment, but then you have like exponentially decay behavior, so you think that everything, that the limit will be scarce.
I'll give you a simple answer. I don't know.
You don't know.
I don't know. It's a heavy tail,
Yeah.
and probably belong to another universality class. So the thing would concentrate on some special places will just contribute tremendously to the distribution. So it would be different behavior. Some records, I mean, some extreme distribution. So I don't think it's another question, another problem. So some local effect, local place, as usual, when you take some of these heavy tail variables, there is one place, if you remove one of them, then the rest will behave nicely.
Perhaps your idea of having this big...
No, then immediately I will get maybe in trouble, because some places will be giving big contribution. So I don't want that. I want it to be kind of what I want.
Any more questions? So, just a question. What happens, for example, can something be done, for example, when lambda alpha d is greater than 1?
So I don't believe that this criteria is precise. So I don't think that one can. So I don't believe that if alpha lambda times alpha d is greater than 1, you will have strong disorder. It's tempting, but it's not true. I believe it's just.
Could be or no?
No, I don't think it's true.
You will never get strong disorder in this exponential moment.
No, in Bernoulli situation, we just showed that you cannot have strong disorder if dimension is large enough. But another, so I think it's technical. I mean, I cannot say. I think that weak disorder can go beyond that. It's just technical.
But do you expect that there exists distributions with exponential moment that would have strong disorder?
Oh, it is known.
That
It is known.
Yeah.
Yes. There are cases where that's what Grigori was saying. If there is a root,
Right.
if the thing has a root, then beyond that it will be strong disorder. But it will not be related to condition lambda time for the. I think it's technical.
Well, if there are no more questions,